Okay, so hope you enjoyed that brief introduction to sampling distributions for means, but we're going to take this look at an example here. And particular moths can infest avocado trees and potentially damage the avocado fruit. The farmer plans to investigate the number of damaged avocado fruit on moth-infested avocado trees of a certain variety. A recent article states that the population distribution of the number of damaged avocado fruit on moth-infested avocado trees of this variety is symmetric, with mu of 6.1 and standard deviation sigma of 1.8. Draw and describe the sampling distribution of the sample mean for the number of damaged avocado fruit, x bar, for random samples of 36 moth-infested avocado trees of this variety from the population. Alrighty, so that was a mouthful. But we need to check our conditions now in order to ensure we have a valid sampling distribution for a mean. So here, it would appear as though we're taking a random sample. So if we're taking a random sample, that will be our first condition, since we have random samples of 36 moth-infested avocado trees. Our center is going to be here, mu of x is going to be closely approaching the mu, which will be 6.1. Now, we can assume that it's 36 moth-infested avocado trees. I believe it's reasonable to assume that there's at least 360 moth-infested avocado trees in this population, or else why would we be trying to find a cure? If it wasn't a problem, we wouldn't be looking for a solution. So I think it's safe to assume there's at least 360 moth-infested avocado trees of this variety. So here at our spread, we're going to have the following. Now, normally we don't know the population standard deviation, but here we are told for the sake of, theory land or math land. So we're going to have sigma divided by the square root of our sample size. And here our sample size is 36. So we're going to get a sigma of about 0.3. Sorry, I had to look down and check my notes here. And now lastly, the shape of our distribution. Well, it didn't say that the population was normal. We were just told it was symmetric. So technically that would meet criteria number 3, which is a no extreme skewness or outliers in our distribution. Another way that we could meet this condition is looking at the sample size here. Well, that sample size is 36, and even if this distribution was skewed, in repeated sampling of size 36, eventually my sampling distribution would be approximately normal. So here we're going to be approximately normal by the central limit theorem, since 36 is greater than or equal to 30. Remember, we want to justify our conditions, and I did not do a great job here on 1 and 2, but hopefully you were following along. So because it appears that all 3 of our assumptions or conditions have been met, we can say that the sampling distribution of x, which is the number of damaged avocado fruit, here is going to be approximately normally distributed with a mu of 6.1 and a sigma of 0.3. So I'd be centered here at 6.1, I'd go up 6.4, 6.77, I'd go down 5.8, 5.5, and 5.2. And I would draw these in normally, but I have not mastered how to do that on this tablet yet. So this is what our sampling distribution is going to look like. So now let's take a look at an example here. How likely is the sample to contain between 5.3 and 6.2 damaged avocado fruits? So let's turn that into a probability statement. So I want to find the probability that our sample is likely to contain between 5.3 and 6.2 damaged avocado fruits. So if I were to, again, to put this on my distribution, that would happen, let's see, 5.3. So 6.4 is about here. So 6.2 is going to be about right here, 6.2. And then 5.8, 5.5, 5.2. So 5.3 is going to happen about right here. So on this normal curve, I'm looking for this shaded area. I'm looking for a between area. Now, I haven't standardized this curve yet, but I can turn these into z-scores. Since our distribution is approximately normal, I won't have to use the t-distribution because we are approximately normal here. So I need to convert these two observations into a z-score. So go ahead and pause the video now and try and attempt to work out these z-scores, and then I'll come back and we'll go through our work together. Okay, so hopefully your answers look like mine or fairly similar. But when I went ahead and converted these observations into z-scores, I got that an observation at 5.3 falls 2.67 standard deviations below the sample mean, and I got an observation of 6.2 falling 0.33 standard deviations above the mean here. So I go ahead and put in these z-scores, and then you can use now your formula table back to the z statistic here to find the probability. So you'd go find the probability of 0.33, and then you would take away the probability of negative 2.67, which 2.67, about right here. And when I find that difference, or if I use technology to find that difference, I find that there is a 62.67% chance that our sample is likely to contain between 5.3 and 6.2 damaged avocado fruits, assuming we are centered here at 6.1 and that all of these other assumptions are met. So that's just how an example of how we can use information about the population to create the sampling distribution and then find out this relevant and correct probability. Part C here is just a fun little throwback to good old Unit 1 days of describing univariate data. Suppose a farmer decides to treat a crop with insecticide Y, and the following results are obtained for the number of damaged fruits from a total sample of 35 fruits. Describe the distribution, and I'm not going to do this one because it's just a good refresher. But as a reminder, when we are describing data, we take a look at the center. Here we notice there's a skew, so we're going to find the median. You'll want to use n plus 1 over 2 to find the observation. We want to look at anything unusual, such as outliers, gaps, or peaks, and from a dot plot, 2 of those unusual features are easiest to see. So I'm just going to put the first letter, gaps, peaks, or outliers. The GPO, the POG, the GOP, all good there. We want to take a look at our shape, and we have 5 types: skewed right, skewed left, approximately symmetric, which features unimodal, uniform, and bimodal. And then the last thing we want to look at is the spread of the distribution. And here again, since we're skewed, we either could look at the IQR because this is a resistant summary statistic, or what would be easier here would be the range, although the range would give us a little bit of a biased view here since there is slight skewness. Now, so just a little fun refresher there. And then lastly, we have another example here, a favorite of the AP exam, but there were 5,317 previously owned homes sold in a western city in the year 2000. The distribution of the sales prices of these homes was strongly skewed right, with a mean of $206,274 and a standard deviation of $37,881. If all possible simple random samples of size 100 are drawn from this population, and the mean is computed for each of these samples, notice again it's all possible samples, which of the following describes the sampling distribution of the sampling mean? So I'm going to go ahead and label my knowns. So here I know that we are skewed right. I know that the mean here for this population was 206, 274, and the sigma was 37,881. And it looks like this is my population here. So this is going to be my capital N. It kind of looks like a W. This is going to be my capital N, which represents here my population size. Now my sample size here is going to be at lowercase n is 100. So notice my population size is capital N, my sample size is lowercase n. So now that you have these variables, go ahead and create the sampling distribution for the sample mean here. Okay, so again, hopefully you were able to find the correct parameters here by the central limit theorem. Since we have a sufficiently large sample size, our sampling distribution is going to have an approximately normal shape, meaning it would be symmetric and unimodal. Because we took simple random samples of size 100, we'd have an unbiased estimator of the parameter. So our mean of the sampling distribution would be closely centered to the population mean here at 206,274. And then lastly, since our sample size of 100 is definitely less than or equal to 10% of 5,317, we can assume independence among our observations. So now we have the correct spread here. And when I find the sampling distribution standard deviation, it comes out to about $3,788.10. So our sampling distribution here for our sample mean, x bar, is going to be approximately normal. And then with these two parameters filled in, there's large numbers. I don't want to say it again. Sorry, having a lazy moment. But you would write these numbers in for their respective colors. And that's just some more examples of how we can use information about our sample to make some inference about the population using the sampling distribution for means. So I guess I'll see you all for the next lesson here in confidence intervals for a one sample mean.